Triangular neighborhood networks can be structured into pipes, and then the pipes can be structured into weird and wonderful structures. Here's an example. It's very complex. What we'll do is we'll work our way up from the simplest construction of pipes to something as complex as this structure. This is a short pipe. Pipe is a piece of the ground state, in this case shown in orange, that's closed on itself in one dimension. In this case, the ends of the pipe happen to be open. Pipes have the property of circumference and length. In this case, the circumference is shown by a purple band. Pipes also have the property of style. This, as shown by the purple elements, is a banded pipe because the elements come around in a circle. In previous videos, we've seen vertical pipes where the colored stripe would run this way, and then there are also pitched pipes. Pitched pipes can be of a right-handed variety or a left-handed variety. Now I've introduced the structure to end one end of the banded pipe. This is done by making 6 5-edge nodes and 1 6-edge node. You see, this is a rather blunt way of terminating the end of a pipe. Now I've reduced the circumference of this banded pipe from 6 to 5, and this changes the construction of the tip of the pipe. Now there are 5 5-edge nodes and 1 5-edge node. So all told, there's a curvature of -6 here. And then, of course, if we were to put the same end here, then this would satisfy Euler's rules for an isolated object. But in general, pipes are connected to some other part of the system. But what I was concerned with in this case and the previous case of the 6 circumference pipe was, how do pipes lengthen themselves? That is to say, we know that defect motion has the effect of carrying structure along with it. And so if there were a constant stream of defects coming down the pipe, how would this end look as those defects moved to this point here? And then how would the pipe grow? So this was the question that I was addressing recently. Well, you know how it is. You play around with things and you make things in this case, and you don't understand what the thing is for, why. So when I was playing with the second level structure for a simple tetrahedron, I managed to build a structure that looks something like this. And for whatever reason, I added this nose cone, one could think of it as, to this thing. And then at some point I realized that there was a face down here, down in here, a triangular face. And so I stuck this pipe, this 3-edge circumference pipe in light blue on. And it stayed here in my lab for a month or two. And I didn't know what it would be used for. I mean, I was intrigued by the property that something that started here could go through the toroidal hole and exit here. And so this sort of looked like the nose cone of a satellite coming back to Earth. Of course, they come back this way, but that's a different story. In any case, this thing just sort of sat there until just yesterday when I realized, oh my goodness, if I'm concerned with the question of how do pipes grow, maybe this is the bullet head of the pipe. I don't know. This is just an idea, okay? But the problem, of course, is that, we could scale this up by 1, and that would make this 3 pipe here a 6 pipe, but that would make the whole object larger. So I didn't want to go and reconstruct the model. What I found was a way of doing something different. I think I've shown you before how it's possible to convert one circumference of pipe, this happens to be a banded pipe here, which is the same as we have here. So in this case, I've been able to enlarge the circumference of the pipe from a 3 circumference to a 6 circumference. And this is done quite easily, as you've seen before. There's a 7-edge node here. Oh, I should really color this something different. That would show you. Okay, I'll stop here. So this is much better. I've just recolored a couple of edges. And so now there's a 7-edge node down here that starts the expansion of the 3 circumference pipe. And each stage it gets larger. So this is 3, 4, 5, 6. And in order to stop, and it would continue expanding the pipe as long as you wanted to make the circumference as large as you want. But here you place a 5-edge node, and this stabilizes the circumference at 6. And so now we have a fairing for changing a 3 pipe into a 6 pipe. And I'll do that as the next section. So this shows very nicely how you can just concatenate these different features together. So here's the new and improved head of the, we can now think of it as the beginning of a tunnel boring machine. And so I've now attached this fairing to the original 3 pipe here. We could shorten this if we wanted to. You can do anything you want. So now we can consider the question of, well, how does the structure get to this point? And I'll show you something about that in the next section. So here's one might think of it as a systolic structure. What we have here is the structure that has a 6 circumference banded pipe at one end and a 6 circumference banded pipe at the other end. So this unit could be stuck anywhere along, in this case, a 6 circumference pipe on either end. But let me show you once again how these things work. Actually, I think I want to go this way to look at the structure. So here's the pipe. I do this because I'm left-handed. I hold things in my right hand and I use my left hand to do the pointing. So here's a 7-edge node that starts the expansion of this 6 circumference pipe to something larger. And you notice that there are 3 such things, 7-edge nodes at the same place in the pipe. So simultaneously, the pipe begins to expand on 3 levels, and this indicates that the expansion goes on for 2 units, and over here it goes on for 1 unit, and then it goes on over here for 1 unit too. So once we get to, well, at this point, these 2 expansions stabilize, but this expansion continues. But when this expansion is finished, what we have is a 10 circumference banded pipe. And then on the far side, if we want to close this down, we can put in a 5-edge node here, and that starts its contraction of the circumference of this section of the pipe. And then later on, there's another contraction going on here for 2 units, and then we wind up with a 6 circumference pipe here. So this is a slug of structure. There are 5 defects, 3 on this end and 2 on this end here. And how this thing moves, let's say in this direction, let's say there's an impinging source of defects coming this way from the sun, from a star. So that the effect of these defects coming this way in great profusion would be to, I hope, force this structure either to get bigger or to move along this pipe. So that's why I use the word systolic to begin with. This is what happens, one can imagine, in the blood vessels. The effect of the defects is to expand and contract this slug of structure, and hopefully move it in this direction. So now, what I'll do is I'll concatenate this structure onto the previous thing that we had. So now we've almost got our tunnel boring machine put together. So this is the head that one might imagine would help to extend the pipe in this direction. And it can be scaled up, and this could be a 6-pipe as such. Here we have the fairing that we've used to change the 3-pipe into a 6-pipe. And here we have the slug of structure, which is the delivery of the new sections of the tunnel, the structure that needed to extend the pipe onwards. So this shows you very nicely how these structures, these defect organizations, can be concatenated with each other, and how you produce different effects from the triangular neighborhood networks. So the only real question that remains to be answered is, as it is with the tunnel boring machines, where is this thing going to go, and how can it be guided to the right place, whatever that is. So let me just, in the next section, introduce the question of how pipes interact with each other. Here we have 2 short sections of 6 circumference banded pipes that are interconnected by means of a short 3 circumference pipe. There are 3 states of rotation of this banded pipe. This is one, and then I'll show 2 other rotations in the next 2 sections. This is the second rotation of the interaction of 2 pipes using a 3 circumference interface. So this is the third rotation of the 2 sections of banded pipe. You see now the pipes' directions are running parallel to each other. So this is rather nice, because we can imagine this pipe here, the cross pipe, moving along in a particular direction, let's say in this direction. So what we have are 2 banded pipes that are constrained as this cross pipe moves along, let's say in this direction. So if we start once again with the head of the tunnel boring machine, go through the fairing to the systolic structure that brings structure forward towards the head of the construction of the pipe. Now we see the attachment of the pair of pipes here. Now, if we consider that this pipe is a pipe running between one star way to the right here and another star here, then this connection here acts to guide this pipe here towards some goal. The goal would be the star that's at the end of this pipe here. So this is a way, using the triangular neighborhood network structure, to explain how light from a distant star can use the existing structure of the connection of stars to form a new connection from a very distant star to a star closer to us. So now I'll take this construct mechanism that I've shown here and do it in a logical fashion, which I think will be clearer and certainly more concise. But you do understand, I hope, the power of the concatenatability of the triangular neighborhood networks idea. I mean, whether these things are real or not, I certainly don't know. Simulation can tell us whether they're real and how organic looking they actually are. But the important thing here is this connection between an existing light pathway and the extension of a light pathway from some other source potentially, but going to the same target as this pipe went to. That's important. That solves many, many, many problems. Now let's look at this process logically. Supposing we have our sun, which is a star, and our planet, which is revolving around that star. Supposing sometime in the distant past there was another star or galaxy here, and it was created at a certain time in the universe and started to emit light. It would emit light in all directions, of course. But in particular, let's consider it emitting light towards our star, and also towards a star or galaxy in further away. So in the time that the light would go from here to here would be equivalent to the time for the light to go from here to here. But it's also true the sun, if this sun came into existence at the same time, then it would begin to emit light and it would travel by some set of means towards this star galaxy here. So this is light from a distant star or galaxy. So consider the idea that we saw in the construct of the tunnel boring machine. Consider that as this star or galaxy is sending light in all directions, and particularly in this direction here, that it would join through a pipe to the light pipe that was going from this star here to our star. So this connection here would act to guide the formation of this pipe from this more distant galaxy as it went along, following the path that this star was following. Now, it may be that there's all sorts of hopping and skipping and jumping as we go from galaxy to galaxy as this light pipe is constructed, but let's not complexify the situation too much. So sometime later in time in the universe, the expansion of the universe, the light from this star or galaxy would be here in terms of getting to our star, and the light from this more distant galaxy would only be here. But of course, because of the pipe joining the two light pipes together, this thing is being guided along the same path that this took. And then at a somewhat later time, still, the light from this galaxy or star would have reached our star, and on Earth we'd be able to see this star or galaxy. But the light coming from this more distant galaxy or star would not have yet reached us, but it's being guided along the same path that this light pipe followed. And then finally the light would get from the more distant galaxy to us. And that's neat. Given that pipes are the second level of structure, then if we have a triangular node, a three-edge node here at first level, then the pipe that is associated with that each edge has a particular construction. If I recall correctly, when I tried to have a three-way branch using banded pipes, I couldn't find a symmetry. But fortunately, there are vertical pipes, and that's denoted by the edge in light blue here. There's a symmetry there, and so it was possible to make a three-way junction, that is, one pipe splits into two pipes. What you notice is that there's a slight bowing in the structure. There's a slight concavity this way in this structure. But this is a solution to the question, how does a pipe represent at second level an edge that divides, has a node that has three edges coming to it. It turns out there's another solution to the question of how one pipe divides into two other pipes, but it's very unsymmetric. If this is the entrance, just choose it to be that. This is a 7 circumference banded pipe coming in this way. One of the exits is 7 circumference right-handed, no, left-handed pipe. And then the other exit is looks like a 6 circumference right-handed pipe. So two of the exits are pitched, and one of the exits is banded. That's rather interesting. There are several solutions to the question of how do two pipes interact with each other. In this case, this pipe here and this pipe here are banded pipes, each of 6 circumference. So this is a banded pipe. And this pipe is a vertical pipe. You see here, and this is, so this pipe comes in like this. And this structure is fairly symmetric. So this is interesting. So this is the interaction of a banded pipe with a vertical pipe. So this is the rather symmetric interaction of two banded 6 circumference pipes. The symmetry is achieved by this lump of structure here at the intersection, and I guess, of course, by the symmetry here. So there's a triangular face here that could be utilized. This is interesting in the sense that the direction of the banded pipe here, which is in this direction, let's say, is exactly the same as the direction and displacement of the banded pipe in this direction. And the same thing could be said about this. This is a 6 circumference banded pipe here, and the direction is essentially the same here. So this is a symmetric interaction of two banded pipes, whereas the previous case was completely symmetric and the directions of the pipes were completely uniform. Here you see that there's a distortion in the way the pipe moves, that this pipe here, if this is considered to be a pipe, is curved as it passes through this pipe, and in some sense this pipe is slightly curved too. These are two 6 circumference banded pipes interacting with each other in a very strong fashion. So I want to argue that the direction of this entrance here and this exit are slightly displaced from each other, and that the direction of this entrance here and this exit here are slightly displaced, and there's a certain amount of curvature in this. So one of the triumphs of the 20th century was the proposal by Einstein that the light would be curved as it passed by a sun. And in 1919, Eddington demonstrated that this was the case, and then in that way justified Einstein's general theory of relativity. So here's a crude model. I don't really want to suggest that it really is the answer, but so these are 3 circumference pipes. They could be scaled up to be anything you want, and as the scaling occurs, different dimensions would occur. But certainly there's a difference in the approach and exit, entrance and exit of this light pipe here as it passes consider this as a star here that's emanating lots of light pipes in different directions, and that light pipe going from some other star here towards some other place or star or whatever here, that this is, I would like to argue, slightly bent. Now, again, I think it's a function of the scaling, and I'd really have to build models, so we'd have to simulate this in much greater detail. But just because of the symmetry of these junctions here, there seems to be some sort of displacement or curvature, as we saw in the previous case. So I don't want to make too much of this, and yet it obviously was a very important aspect of science in the 20th century. But, you know, so the bending of light in the triangular neighborhood syntax seems also to occur. That's what I want to say. I don't want to put too much emphasis on this, but I think I ought to say at least what I believe. Two pipes can be brought together in an intimate fashion. This is an instance of 6 circumference banded pipe on all 4 entrances and exits to the interaction. There are 3 7-edge nodes, and there are 4 sets of these 7-edge nodes, yielding a total curvature of plus 12, which is 1 toroid's worth. So this is a completely symmetric structure. As I've done several times in the past, I've made banded pipe structures and vertical pipe structures. This is the interaction of 2 pipes that are vertical pipes, as shown by the light blue banding. These are 6 circumference pipes in vertical style, and 2 of them interact. All 4 entrances and exits are vertical pipes. So this is a completely symmetric structure. A single instance of the tetrahedral junction, shown in purple, can be implemented as an infinite lattice, shown here. This is 10 instances of the tetrahedral junction. Each of these junctions is again a 6 circumference banded pipe. The lattice is formed by taking instances of the tetrahedral junction and conjuncting them with 1 band of structure. Of course, this structure can be lengthened. The length of the pipe here can be as large as you want, which creates a much larger lattice. Or we can do scaling, where we replace each triangle with put an extra node in each edge, and that would scale the structure. In any case, what we have in the center of this infinite lattice is a large hole, and if you lengthen the pipes or scale, then the hole gets much larger. In the tetrahedral lattice, the size of the hole in the middle of the lattice is a function of the scaling of the lattice itself. So this hole can be as large as one wants, and into it we can put a structure of any description at all. There are 8 binding sites in this area here that can be used to connect whatever structure we put in here to the tetrahedral lattice. Into the cavity formed by the pink tetrahedral lattice, we can put the first instance of the tetrahedral junction. This purple structure can be itself extended to become an infinite tetrahedral lattice, which is exactly equivalent to the pink lattice. These two lattices can be joined together to form a dual symmetric tetrahedral lattice system. If the very center point of either of the lattices is removed, then we can put into that now empty space volume a particle, an object of any construction. The dual tetrahedral lattice has at its very center an open volume into which a particle of any construction can be placed. My sense is that this is the triangular neighborhood network basis for the nuclear field. In the same way that we use the banded pipe implementation of the tetrahedral junction to form a dual infinite tetrahedral lattice, we can use the vertical pipe implementation shown here also to build a dual tetrahedral infinite lattice. So either of these constructions could be used to form the dual tetrahedral lattice of infinite extent, at which at the center of which is a particle of some construction. In an attempt to try to make sense of the possible utilizations of the two forms of the dual tetrahedral lattices, I've made up this image. Supposing we have a construct of an outer field made of the banded dual tetrahedral lattice and an inner field made perhaps of the vertical dual tetrahedral fields. It should be possible to interface these two field structures on a one-for-one topological basis, and yet the constructions are entirely different. Suppose in the outer field we embed objects which we might call electrons, and in the inner field objects that we might call quarks. This is at least a plausible topological process that we're involved in here, because the dual tetrahedral lattices are infinite in extent, so they can have as much complexity as they need. The objects themselves can be moving around in the fields of their construction, and then in both cases, in the case of the outer field and in the case of the inner field. This is a plausible, possibly plausible construction using the dual tetrahedral lattices, where we use the style of the lattice, the banded style for the outer field, and the vertical dual tetrahedral lattice for the inner field, or vice versa. It makes no difference in that respect. This is the interaction of 3 banded pipes in each of circumference 12, interacting on 3 perpendicular axes using 7-edge nodes. There are 3 7-edge nodes here, and there are 8 such sites, as you can see. This gives the structure a total curvature of 24, which is equivalent to 2 toroidal holes. This structure can be arrayed in a cubic lattice of infinite extent. By placing a dual lattice along these axes here, we can make a dual cubic lattice structure using banded pipe. Like I've done several times in the past, here I've made a vertical pipe implementation of the interaction of 3 pipes, in this case vertical pipes. The vertical pipes use 8-edge nodes as the way of forming their symmetry, the 8-edge node has a curvature of +2. So if we select just half of the curvature, a curvature of 1, then there are 3 such curvatures here, and there are 8 sites throughout the whole interaction. So this structure has a positive curvature of 24, which is 2 torus worths of structure. This construct can be put into an infinite lattice, and then we can build a dual lattice around it. So we then have a dual cubic lattice made in the vertical pipe implementation, just like we had a dual cubic lattice in the banded pipe implementation just previously. So here are the 2 cubic lattices that can be infinite in extent, the banded pipe version and the vertical pipe version. My sense is that these dual cubic lattices are the electromagnetic field. I've always had the feeling that these lattices should be able to hopscotch along, roll along, example for along a pipe. I've not found the construct yet, but my sense is that this should be possible given the construction of the dual aspect of the cubic lattice. So this would be my best bet for what these lattices could be used for.